In front of the Pantheon in Rome, there is a contradiction that is difficult to ignore. The empire that built this structure disappeared. Its engineers died. Its quarries changed. Its trade routes were disrupted. The formula used on the construction site was almost lost. But the dome still rises above the city. It has endured earthquakes, fires, wars, and countless cycles of rain and heat. Nearly 2,000 years later, it remains the largest unreinforced concrete dome in the world. At the same time, bridges, parking garages, tunnels, and buildings constructed in the modern era may require repairs after only a few decades. Cracks appear, water gets inside. Reinforcing steel rusts. Sections of the surface begin to break away. This seems to prove that the Romans simply made better concrete than we do. But that conclusion is incomplete. Roman concrete does not outperform modern concrete in every application. It would not easily allow us to build today's skyscrapers, slender overpasses, or long-span bridges. Its advantage appears in certain massive structures, domes, foundations, walls, and harbors built without steel reinforcement. Even so, something extraordinary happens inside this ancient material. What did the Romans put into their concrete that we stopped using? The answer begins long before Rome. Earlier civilizations were already firing limestone, producing lime, and preparing mortar. Egyptians, Greeks, Mediterranean peoples, and communities throughout the Near East combined mineral materials to bind stones, coat walls, and waterproof reservoirs. Rome did not invent every ingredient. Its transformation came from bringing materials, practical observation, labor, transportation, and organization together on a scale few earlier societies had ever achieved. When limestone is heated in a kiln, it releases part of its composition as gas and transforms into quicklime. This material is extremely reactive. When water is added, it heats intensely and becomes hydrated lime. Mixed with sand, hydrated lime produces a mortar capable of binding stone and brick. In a conventional formulation, this material hardens slowly as it reacts with carbon dioxide in the air. But Roman builders discovered something that changed the rules. Across the Italian peninsula, especially in regions shaped by volcanic activity, ash and fragments of rock possessed unusual properties. One of the most famous materials was associated with the region around Pozzuoli, near the Bay of Naples. That is where the word pozzolan comes from. When certain volcanic materials are mixed with lime and water, the reaction does not depend solely on contact with air. The mixture develops cementitious compounds even in extremely wet environments. It can even harden underwater. That detail transformed mortar into an imperial tool. Builders could now consolidate foundations on difficult ground, line cisterns, construct channels, raise massive walls, and create harbor structures in direct contact with the sea. But there was no single secret formula distributed throughout the entire empire. Builders adapted their mixtures. They used volcanic ash where it was available. In other regions, they searched for materials with similar behavior. Crushed bricks and roof tiles could also supply reactive components. Stone, volcanic tuff, and ceramic fragments were used as aggregates, the solid pieces that gave concrete its volume. A mixture intended for a cistern did not need to be identical to one used in a dome. A harbor required different behavior from an urban wall. The selection changed according to the environment, structural loads, availability, and local experience. That flexibility was one of the keys. The Romans did not possess modern chemistry to explain every reaction. They could not see microscopic crystals or calculate molecular structures, but they observed the results. They noticed that certain ash worked better near water. That lightweight stone reduced the weight of a vault. That crushed brick improved mortar in wet environments. That some mixtures needed more time while others became hot during preparation. The knowledge was born on the construction site, and a Roman construction site was far less clean than the surface of a monument might suggest. Everything began with fire. Workers extracted limestone and transported it to kilns. Fuel maintained high temperatures for hours or days, depending on the operation. After firing, the material transformed into lime had to be handled carefully. At the same time, other groups extracted volcanic ash, broke apart stone, separated aggregates, and collected bricks or roof tiles to crush. Baskets, carts, and boats moved tons of raw material. There was no concrete mixer truck arriving at the site with a ready-made mixture controlled by computers. Teams measured, transported, and combined the materials. Water had to be added. The mass had to be placed and compacted. Roman concrete is known as opus caementicium. The expression describes construction made from mortar and fragments of stone, ceramic, or other aggregates. In practice, it often appeared as a hidden structural core. Workers built two faces of stone or brick, creating a kind of permanent formwork. Between these faces, they placed the mixture in layers. Solid fragments were arranged within the mortar. Each layer needed to fill the voids and form a coherent mass. The exterior wall we see does not necessarily reveal the material responsible for its volume and much of its strength. At Trajan's market in Rome, this logic made it possible to construct a complex development on sloping ground. Corridors, rooms, vaults, and multiple levels were integrated into the hillside. Brick facing provided a finished surface and helped organize construction. Behind it, concrete cores formed walls and vaults capable of distributing structural loads. The baths of Caracalla demonstrate the same technology at an even more monumental scale. Vast halls, pools, service passages, vaults, and thick walls formed part of an infrastructure that had to handle crowds, water, and enormous temperature variations. The concrete was not simply a poured material. It was part of an entire construction system. Masonry faces, massive cores, arches, vaults, buttresses, generous thicknesses, aggregates selected according to their position. That is why attributing all this durability to volcanic ash creates an illusion. Pozzolan matters, but so do geometry, water protection, workmanship, aggregate type, thickness, and the fact that many surviving structures work primarily in compression. And another detail is hidden within the mass. When researchers cut and analyze samples of Roman concrete, they find small white inclusions. For a long time, these spots were interpreted mainly as evidence of imperfect preparation. Perhaps the lime had not been mixed properly. Perhaps workers had left behind clumps. Perhaps it was merely a defect preserved by chance. But microscopic and chemical analyses reveal a far more interesting possibility. These inclusions, known as lime clasts, may be the result of a deliberate technique, or at least a specific method of preparation. In certain mixtures, some of the lime entered in a highly reactive state. The presence of quicklime as the ingredients were combined generated intense heat. This is known as hot mixing. In the best-known method of producing mortar, water is added to quicklime before it is combined with the other materials, converting it into hydrated lime. Under the hot mixing hypothesis, at least some of the quicklime participates directly in the preparation alongside the dry ingredients, either before or during the addition of water. When the water arrives, the reaction rapidly releases heat. Areas within the mixture reach high temperatures. This accelerates certain reactions and creates chemical environments that do not develop in the same way during an entirely cold preparation. Calcium-rich fragments may also remain distributed throughout the matrix. That is where an apparent imperfection becomes a defense mechanism. Imagine a small crack advancing through the concrete. It encounters a lime clast. Later, rain or moisture penetrates the opening. The water reacts with the calcium-rich material. Part of it dissolves and moves through the crack. Calcium compounds can then recrystallize inside the empty space. The crack activates the very material required to close it. In laboratory tests inspired by these formulations, researchers produce samples containing lime clasts, create cracks, and force water through the material. In certain samples, the openings are gradually filled by new mineral products, while comparison mixtures do not display the same behavior. This is self-healing, but it is not unlimited regeneration. A wall split in half does not return to its original condition. A displaced foundation does not correct its own geometry. Major structural failures remain dangerous. The mechanism is valuable primarily because it can seal small cracks before they become permanent pathways for water and aggressive agents. In a thick material, every sealed microcrack can prevent a much larger sequence of deterioration. The technique also did not need to be applied identically in every Roman structure. Formulas varied, quality varied, historical periods varied, and scientific interpretations continue to be refined as new samples and preserved construction sites are studied. Even so, the white clasts no longer appear to be mere mistakes. They may be microscopic reservoirs for repair. But the most surprising test does not occur on land. It happens in the sea. Throughout the Mediterranean, the remains of Roman harbors are still exposed to waves. Piers, breakwaters, and concrete blocks have faced salt water for many centuries. For a modern, reinforced concrete structure, this environment is extremely aggressive. Water enters through pores and cracks. Chlorides from the salt advance through the matrix until they reach the steel. Once the protective layer around the reinforcement is compromised, the metal begins to corrode. Rust occupies more volume than the original steel. This expansion places pressure on the concrete from within, opens new cracks, and can force entire sections of the concrete cover to break away. The process creates a cycle. More cracks allow more water to enter. More water accelerates corrosion. Corrosion produces further expansion. Many Roman maritime structures do not face this mechanism because they contain no reinforcing steel. They are masses of mortar, aggregates, and rock working primarily in compression. That does not mean removing steel would solve every modern problem. Without reinforcement, concrete performs poorly under tension, the forces that attempt to stretch or bend a component. Bridges, slabs, and slender beams depend on steel precisely because it resists those forces. Roman piers play a different game. They are large, heavy, massive. Their geometry reduces the need for thin elements working in flexure. And certain maritime mixtures offer a second advantage. Seawater does not function merely as an enemy. It participates in slow reactions involving volcanic ash, lime, and aggregates. As it circulates through the pores, it dissolves certain components and encourages the formation of new minerals. Among the products identified are crystals of aluminous tobermorite and philipsite. The names may seem far removed from a construction site, but their effect can be visualized. Imagine a network of crystals slowly growing within the material's internal spaces. Instead of merely removing components and enlarging voids, certain reactions create new mineral bonds inside the matrix. The concrete continues to transform. This does not mean that all salt water strengthens every type of Roman concrete. Its behavior depends on the composition of the ash, the aggregates, the proportion of lime, the porosity, and the environmental conditions. Nor does it mean every ancient harbor remains intact. Many suffered erosion, collapse, ground movement, and human destruction. We primarily observe the structures that survived, creating a kind of natural selection among the strongest examples. Even with these qualifications, the chemical difference is extraordinary. In modern reinforced marine concrete, saltwater intrusion can initiate the corrosion of steel. In certain Roman mixtures, water circulation contributes to slow mineral evolution. One attempts to keep the external environment completely outside. The other can survive by interacting with it. But no structure demonstrates the combination of material and design better than the Pantheon. Its current form was completed during the reign of Emperor Hadrian in the 2nd century. Upon entering, visitors encounter a circular space covered by a dome approximately 141 feet in diameter. At its summit is the oculus, a circular opening roughly 30 feet wide. There is no glass. Light, air, and rain pass through the void. The first reaction is to wonder how the concrete remains suspended without a modern steel framework. The answer does not lie in a single formula. The dome works primarily in compression. Its curved form directs the loads toward the base and into the drum, the enormous circular wall supporting it. That base is thick. It contains niches, relieving arches, and massive piers integrated into the structure. The mass is not distributed randomly. As the dome rises, its thickness decreases. The builders also changed the aggregates. In the lower sections, where the loads were greater and the structure needed mass and strength, denser materials were used. In the upper regions, lighter aggregates appeared, including tuff and pumice. Pumice is a volcanic rock filled with tiny voids. It weighs far less than compact stone. Placing it near the top reduced the load that the entire structure below had to support. The oculus completed the strategy. It illuminated the interior, but it also removed material from the very top of the dome. Instead of closing the highest point with additional tons of concrete, the builders left an empty circle. The coffers, the geometric recesses visible across the interior surface, helped reduce some of the mass and visually organized the monumental scale, although their structural effect alone does not explain the dome's survival. The dome remains standing because multiple decisions work together. Appropriate concrete, sufficient thickness, graded aggregates, compression-based geometry, a massive base, intelligent weight distribution. If the Romans had used the same mixture in a very thin dome with inadequate support and heavy aggregates extending all the way to the top, the result could have been collapse. Chemistry prolongs the life of the building. Geometry allows it to exist. That raises another question. If this technology works so well, why did it stop being common? The knowledge did not disappear in a single night when the Western Roman Empire fragmented. Masons continued working. Lime mortars remained in use. Roman techniques survived, changed, and blended with regional traditions. Major structures continued to be built in the Eastern Roman Empire. What diminished across many Western regions was the system capable of supporting monumental construction on a Roman scale. Large public commissions became less frequent. Transportation networks lost their regularity. Certain materials stopped traveling over long distances. Quarries, kilns, and ports no longer operated within the same political and economic organization. The type of construction required also changed. A smaller city did not need baths capable of receiving crowds. A regional ruler did not possess the same resources to maintain teams, suppliers, and specialists. Without a continuous sequence of monumental projects, some practical knowledge was no longer transmitted in a standardized form. It was not merely a formula that disappeared. It was the chain connecting the quarry, kiln, ship, cart, workforce, and administration. Centuries later, another revolution transformed construction: Portland cement. Produced industrially from raw materials heated to extremely high temperatures, it made it possible to create a standardized, predictable binder capable of developing strength quickly. Mixed with water, sand, and aggregates, it forms modern concrete. With steel bars inside, it becomes reinforced concrete. Concrete performs exceptionally well under compression. Steel carries much of the tension. Together, they make possible thin slabs, beams, slender columns, bridges, dams, tunnels, and skyscrapers. A Roman could not simply reproduce this performance using the Pantheon's mixture. Modern concrete can also be extremely durable when designed, produced, installed, and maintained properly. Some formulations use supplementary cementitious materials, low permeability, and rigorous crack control. The problem is not inevitable inferiority. It is a difference in priorities. Portland cement provides high early strength. That allows formwork to be removed sooner, schedules to move faster, and structures to enter service quickly. Industrial production provides control and repeatability. Steel makes it possible to use less mass while spanning greater distances. But speed can bring compromises. Inappropriate mixtures, excess water, insufficient curing, and pressure for productivity increase cracking and permeability. Inadequate concrete cover over reinforcement makes it easier for aggressive agents to reach the steel. Construction errors drastically reduce service life. Massive Roman concrete cures slowly and does not depend on an internal network of steel vulnerable to corrosion. In certain formulations, its reactions continue for extended periods. But it also requires thicker walls, large volumes of material, and geometries compatible with its low tensile strength. Therefore, comparing only the age of the Pantheon with that of a modern bridge is unfair. A bridge faces moving loads, vibrations, desing salts, thermal variations, and flexural forces. It must be slender and economically viable. The Pantheon is a massive structure protected in large part by finishes and maintained throughout history. We also see the Roman works that survived. Those that collapsed left less evidence and rarely appear in popular comparisons. Even so, the provocation remains valid. Why are so many modern structures optimized to gain strength quickly, but not given the same attention to ensure they continue changing beneficially for centuries? That question is leading researchers back to the ruins. Ancient samples are removed from structures and analyzed using microscopes, X-ray diffraction, spectroscopy, and other techniques. Each instrument reveals a different scale. Microscopes reveal cracks, pores, and clasts. X-rays help identify minerals. Spectroscopy analyzes how the elements are combined. Chemical models reconstruct reactions that begin on the construction site and continue long after the building is completed. Researchers also produce mixtures inspired by ancient materials. They compare hydrated lime with quicklime. They create calcium-rich clasts. They fracture samples. They force water through the cracks. They observe which openings remain clear and which receive new mineral deposits. The results indicate that principles of hot mixing may encourage limited self-healing. That does not mean resurrecting a single formula and pouring it onto every modern construction site. Volcanic ashes vary significantly. Materials available near Naples may not exist in another region. Roman concrete develops strength differently. Many modern projects require steel, pumping, dimensional precision, and early performance that ancient formulations cannot provide. The opportunity lies in adapting the principles, creating mineral reservoirs capable of sealing microcracks, using pozzolanic materials to replace part of the Portland cement, designing concrete that interacts with moisture without deteriorating rapidly, extending service life to reduce repairs, raw material consumption, and interruptions in use. Every bridge that lasts longer avoids new construction. Every crack sealed before it reaches the steel reduces maintenance. Every ton of cement saved can reduce the environmental impact of construction. The Roman lesson is not to return to the past. It is to recognize that hardening quickly and remaining durable are not exactly the same goal. We return to the Pantheon. Light enters through the oculus and moves slowly across the dome. The surface appears motionless, but at the microscopic scale, the concrete tells a different story. Its secret was never a single magical ingredient, it was a system. Lime produced by fire, volcanic ash and rock, aggregates selected according to their purpose, mixtures adapted to the environment, thick walls, geometries that work in compression, time for the reactions to advance, and in many structures, no internal steel vulnerable to corrosion. In harbors, seawater participates in mineral evolution. In some land-based mixtures, lime clasts provide material for sealing small cracks. In the Pantheon, progressively lighter aggregates reduce the weight of the dome. At Trajan's Market and the Baths of Caracalla, concrete, brick, arches, and vaults work as parts of a single architecture. Roman concrete is not perfect. Not every mixture survived. Not every building remains. It does not automatically replace reinforced concrete, and it cannot meet the demands of contemporary construction on its own. But its finest works reveal an idea that modern speed frequently pushes into the background. A material does not need to stop evolving once it hardens. The Romans did not manufacture perfect concrete. They manufactured concrete that continued changing after construction ended. If you enjoyed this video, subscribe to the channel now so you do not miss the next stories. And tell me in the comments, what city are you watching from? Take care, and I'll see you next time.